Thanks much for inviting me to this workshop. Today, I'd like to focus on attention, variance, and context for fine-grained recognition. In natural world recognition, such as species identification, the difference between two species can be very subtle. Shown here are two instances from the wonderful iNaturalist dataset. The key difference is the number of tiny black dots on a ladybug. Not only such a fine-grained categorization can only be provided by human experts, but it also leads to a large number of categories with highly imbalanced, long-tail distributed observations for different categories. About 1.2 million species have been documented, with more species to be discovered in the wild. Let me first focus on the open long-tailed recognition problem. The long tail means that the majority of categories contain only a few instances. The challenge is how to leverage many head instances and generalize discrimination from the few tail instances. The open-ended recognition also requires sensitivity to novel classes. This sensitivity could be at odds with robust generalization from very few tail instances. Finally, as much focus is placed on recognizing the majority tail categories, it is easy to forget what distinguishes the head classes. Eventually, though, the head performance is what matters most often in the real world. These three aspects have been studied in isolation. Imbalanced classification tackles lopsided data size differences that could derail discrimination. Few-shot tackles learning from small data, whereas open set recognition handles out-of-distribution detection. Their proposed techniques assume different training and testing settings, and the real challenge here is to address all three problems in the same setting. We propose a feature learning model with memory and attention as key components. Consider a tail class instance. It would activate different memories of what the model has seen with the head, body, and the tail features. These associated memory features could be used to enhance the direct image feature. With a few training instances in the tail, we are able to learn the right attention to selectively enhance the feature for best discrimination. We compare the final feature to the memory, which captures the totality of our training data. A final decision can thus be made with respect to both open and closed classes. Our model delivers significant gains over major benchmarks, including 2% accuracy gain over the 1 million fine-grained face recognition benchmark. We extend our memory and attention idea to domain adaptation. The basic setting is closed world recognition from a source domain with the labeled training data and a target domain with unlabeled test data. For instance, training data are collected in the sunny weather, whereas the model needs to be applied to data collected in the rainy weather or in several other weather conditions. We consider a new setting where there are no such discrete domain tags. That is, the target domain could contain mixed, unknown, or continuous domains. We also want to evaluate the model directly on open, unknown domains without seeing any data. Our idea is to first disentangle the feature into those indicative of the class and those indicative of the domain automatically. We can then rank each instance according to its distance to the source in the domain feature space and recruit the instances near to far in a curriculum for adapting the source model gradually. Such a model could also be very useful for fine-grained recognition to propagate precious human expert annotations from one dataset to another. Let's take another look at the closed world long tail recognition. How can we recognize something that we have rarely encountered? I would liken it to rare disease diagnosis. When the doctor gives an ambivalent diagnosis, we seek a second opinion across the globe. If two doctors' diagnoses remain inconclusive, we seek a third opinion. The more diverse these doctors' training backgrounds are, the more confidence we have in their consensus. We deliver a model just like that for long-tailed recognition, but from a principled model bias and variance analysis perspective. Traditionally, bias and variance analysis is formulated for regression problems. For example, fit a line to predict y from what x given observed points with a paired x and y coordinates. The first thing is that whatever training data we have, it is just a subset snapshot of all the possible data out there. Each boxed plot here contains one such data set of 2D points generated as samples of the gray line with additive random noise. The red line is the model fitted to the training data. We can dump all the individual data sets and their models in the same plot. The prediction error on any point depends on which red line we use, and that depends on what training data we have. It turns out the expected prediction error can be decomposed into 3 terms. First is the irreducible error in the measurement noise, which we can do nothing about. 2 is the model bias between the average line model and the gray line ground truth. And 3, the model variance on how much the red lines fluctuate from their average. The bias measures the model accuracy, whereas the variance measures the model stability as the training data varies. The bias and the variance concept can be expressed entirely in the loss function. For regression, it is the L2 loss. The key is to calculate the mean model, which minimizes the loss with respect to the data set. The model bias is simply the loss between the mean model and the ground truth. And the model variance is the expected loss with respect to the mean model. For classification, we just need to replace the L2 loss with the 0, 1 loss. The mean becomes the most often or the main prediction. If we have 20 predictions made by 20 models derived from 20 training sets, the mean is their majority prediction. By creating sampled subsets from the training data, we can empirically evaluate the bias and the variance of each method. Now let's examine how long-tail classifiers fare with respect to the vanilla baseline, which just collects cross-entropy losses over individual instances. The large, medium, small circles indicate the head, body, and the tail performance numbers. We are only interested in how much the performance is above or below the diagonal line, where the 2 methods are on par with each other. We pick LDAM as a representative leading long-tail method. By design, it boosts the performance for the tail and body. However, it loses head performance, just like other long-tail methods. Our approach, named the RIDE, boosts the accuracy across the entire class spectrum with noticeably better head accuracy over the baseline. In terms of the model bias, LDAM reduces most bias on the tail, and our RIDE is able to further reduce the bias. In terms of the model variance, LDAM, like all other long-tail methods we have tested, invariably increases the variance. That is, even though the long-tail method could deliver a better accuracy on the tail, the resulting model fluctuates more with the training data, whereas our model is able to reduce the fluctuation to be less than the baselines. So how do we do it? To reduce the model variance, we take the well-known ensembling approach. However, our ensemble is special in that our multiple experts share the same training data and the same backbone with independent classification heads. To further reduce the model bias, each expert is trained not only to optimize the classification performance, but also to collectively diversify more among them as the training instance comes from the tail end of the class spectrum. The usual ensemble approach increases the overall model size and the runtime compute. For us, at stage 1, we train all the backbone shared experts with minimum extra costs on their classification heads. To reduce the runtime compute, at stage 2, we train an expert router to decide whether to seek another expert in the cumulative decision process. Our results show that most instances in the head classes only need one expert, whereas most instances in the tail classes need 3 experts. Our approach achieves SOTA on major benchmarks with a large margin. It is also a universal add-on that boosts performance consistently with various backbones, long-tail algorithms, and training schemes. On the fine-grained iNaturalist 2018 validation set, there are only 3 test instances per class. We examine the distribution of categories according to how many each model predicts correctly. Our model significantly increased the number of all 3 instance correctly classified categories. The reduction gap with the prior art BBN and the vanilla baseline cross-entropy method is larger on harder categories. BBN gains the tail accuracy by 8% compared to the cross-entropy baseline, but it drops a significant 23% on the head classes. Our method, though, performs evenly. That is, on average, it gets 2 out of 3 test instances correct for head or tail classes, a very desirable property for long-tailed recognition. Let's get back to fine-grained recognition. Natural learning of vision in babies faces exactly the same problems. But babies have no sense of semantic categories, only a sense of instances she interacts with. The baby vision turns out more flexible and generalizing than today's machine vision. We formulate maximal instance discrimination instead of categorical discrimination as the goal of unsupervised feature learning. It leads to many contrastive learning methods, such as SimClear and MoCo. Instance discrimination presumes that items in our visual world are all different. But how do we go beyond that and see that different items could actually be of the same kind? The baby step towards developing categorization is to discover natural grouping of different but similar instances, such as Xi and Xj. By instance discrimination, Xi repels Xj and attracts Xi with prime, which is an augmented version of Xi. Based on our own engineered group of Xi and Xi prime, we would like to discover natural group of different instances, Xi and Xj. We capture natural visual similarity with a local feature grouping. Now, Xi attracts Xi prime's group centroid and repels other group centroids. Xj is likely to attract and repel the same group centroids. Since Xi and Xj share similar attraction and repulsion patterns, they will be mapped to similar positions in the feature embedding space. Schematically, given instance Xi, we generated two augmented views. We compute their features and contrast them instance-wise with the memory bank. We compute a separate feature branch and conduct local grouping within each mini batch and calculate group centroids. We contrast the instance feature with the local group centroids in a cross-level discrimination fashion. Our model beats SOTA on high correlation, high long tail, and balanced benchmarks, as well as transfer learning, semi-supervised learning, all with a much smaller academic compute. Let's get to the last issue of learning fine-grained differences from small data. Two aspects could be very helpful. One is spatial attention onto the foreground of interest. The other is a visual context of co-occurring backgrounds, especially when the foreground is small or ambiguous. Our feature learning-based segmentation method could capture both objectives. We have extended image-wise discriminative feature learning to pixel-wise discriminative feature learning. We first group pixels into segments in the feature space. And we then turn the original image-wise discrimination into data-driven feature-evolving segment discrimination. Given an unlabeled image collection, we are able to segment each image and discover clusters of fragments such as hairs, faces, upper body, helmets, and so on and so forth. They correspond to semantics without names. Our learned pixel-wise feature captures not only what the object each pixel is a part of, but also the visual context it is embedded into. Based on the pixel-wise feature, we can retrieve a pedestrian crossing a semi-empty intersection, a pedestrian passing by a vehicle, a bike rider, a motorcyclist in a back view, or a parked motorbike. Such contextual annotations are not available during training. Even if they are, it will be hard to specify the context vocabulary ahead of the time. Yet we can discover these visual contexts in a purely data-driven manner. We have extended our work to weekly supervised segmentation, providing a unified contrastive learning method, whether the weak supervision is coarse in terms of image tags or bounding boxes, or sparse in terms of points and scribbles. We are able to deliver SOTA performance in each week supervision camp. And there are more significant gains as scribbles shrink their lengths to even sparser points. Our current work in progress is on unsupervised hierarchical image segmentation, where we can discover scenes and their components in the pixel-wise feature itself. We obtain significant gains on unsupervised semantic segmentation benchmarks. Segmentation breaks down an image into its natural structures. With videos, we can find the moving foreground directly. Our latest two-frame-based approach is able to learn foreground extraction without any supervision. With the invariant representation, regardless of the distracting background, we can learn a simpler and yet more generalizing policy through standard reinforcement learning. The same idea can be extended to fine-grained recognition. To summarize, there are three key issues in fine-grained recognition. To discern fine-grained differences, We propose pixel-wise feature learning for segmentation to capture spatial attention and visual context. To handle extremely imbalanced long-tailed data, we propose featural attention and a model bias and variance perspective to create memory-enhanced features and a diverse expert ensemble. To handle open classes, we propose the use of visual memory and exploit data correlation in unsupervised feature learning. Finally, I'd like to thank my students, postdocs, and collaborators for the joint work. And I thank you for listening.